In a pipe with an adjustable length that's open at both ends and filled with air, a tuning fork resonates when the pipe is 44.7 centimeters long, but does not resonate for any smaller lengths. Since it doesn't resonate for any smaller lengths, that means that the 44.7 centimeter length corresponds to the fundamental frequency. So the first thing that we need to figure out is what is the wavelength, because in order to eventually calculate the frequency, we need to use the equation that relates the speed, wavelength, and frequency rearranged for f, which is f is equal to v over lambda. We know the speed of sound in air is 343, but we don't yet know this wavelength. So let's use the formula for the wavelength in an open tube, which is the one you derived in the lab, and is also in your notes, 2L over N. So for the fundamental frequency, the N is just equal to 1, so it's just 2L divided by 1, so that denominator will just go away. So we just have 2 times L. The length of the tube is 44.7 centimeters, which I'll convert to meters, 0.447. That gives you the wavelength, which you would then plug in down here, and that gives you the frequency, which, when rounded to the nearest integer, you should get an answer of 384 hertz. And that was for part A. In part B, it says determine two other lengths at which this pipe will resonate with this same tuning fork. So the tuning fork has the same frequency, the speed of sound is still the same, which means we're still looking at the same wavelength. So the only difference now is, in this formula, wavelength equals 2L over N, we found the resonant length for the fundamental frequency, but we can find it for the second and the third harmonics. So if I take this equation and rearrange it for L, so L is equal to N lambda over 2, you can find a whole bunch of other lengths, but let's just look at the next two lengths after the fundamental, which would be the second and the third harmonics. Just plug in N equals 2, which would cancel out with this 2. So the second length that will work is just equal to whatever the wavelength was, what you calculated up here. And then the third length that will work is if you just plug in N equals 3. So you have 3 times this wavelength divided by 2, and you'll get another length. The two answers I got were 89.4 centimeters and then 1.34 meters. And in part C, so now we're going to seal off one end of the pipe. So it is a closed tube, and describe what changes happen with the same tuning fork. So we still have the same frequency, since it's the same tuning fork. Speed of sound is still the same, which means the wavelength is still going to be the same. Whatever we found back in part A for that wavelength, the 0.894, that's still going to be the wavelength, but now we're looking at the formula 4L over N instead of 2L over N, because it is a closed tube. So when you rearrange this for L, you get L is equal to N times lambda over 4. So you can plug in the fundamental frequency. You're just going to plug in N equals 1. So it'll be that original wavelength, the 0.894, divided by 4 to get you your first harmonic. Now remember, when you have a closed tube, only the odd numbered harmonics exist. We showed in the lab that based on the formula you come out with, you cannot have N as an even number. And that's for the closed tube. So the next harmonic in which the tuning fork will resonate is when N is equal to 3, not N equals 2. So 3 times the wavelength divided by 4. You should get about 67 or so centimeters for that one. And then no fourth harmonic. And then the fifth harmonic, you plug in 5 times the wavelength over 4, and you'll get 1.12 meters. And for part D, you just want to replace the air with helium and describe an experiment that uses the pipe to determine the speed of sound in helium. You basically are doing the exact same thing you just did in the lab last week, which is you use a bunch of different tuning forks. So you're going to have multiple frequencies. And for each of those, you want to measure the length of the closed tube for the fundamental frequency for each of those different frequencies with the different tuning forks. Just want to get the fundamental frequencies. We don't care about the second and third harmonics of all those. And then you can graph. I guess first thing you have to do is figure out the wavelength, which for a closed tube we said was 4L. So now you can just plot according to this equation, lambda equals V over F, if you match that equation with y equals mx plus b. On the y-axis, you can plot the wavelength. On the x-axis, you can plot 1 over the frequency, and then the slope of the graph would be the speed of sound in helium.